In this video, we're going to take a look at this example, which is on hypothesis testing of population proportion. Now, this one says, a beverage producer purchases their brown glass bottles from GBC. However, they purchase their caps from another supplier. Prior to using a shipment of these caps in their bottling process, they inspect 500 of them. Each inspected cap is classified as defective or non-defective. Well, this is an indication that the whole population is divided into two groups, successes or failures, basically. And the producer has agreed with their supplier that the true population defective should not exceed 0.04. So 4% is the maximum defective that they accept from the supplier. They want to perform a hypothesis test to determine if the true population does in fact exceed 0.04. They wish to use the inspection data to perform an appropriate test using a level of significance of 0.1. Well, 0.1 is our alpha, and this is a very common application of hypothesis testing in quality control, where you take a sample of supplier shipments, and in this case the sample is 500 caps, and you inspect that sample and you extend the result of the sample to the entire shipment using hypothesis testing. So in this case, they want to make sure that the population defective, or in this case a proportion, is not over 4%. So here you see that the key statement that tells you what type of test are we doing here is here. Does in fact exceed 0.04. So we're looking at a null hypothesis that says population proportion is 0.04. And again, this is not average or population mean. It's not mu. It's proportion. And try to distinguish that distinguish proportion and mean. This is population proportion is going to be more than 0.04. That's what they want to test. So if the alternative hypothesis basically wins and we reject the null hypothesis, that means they would reject the entire shipment from the supplier because the test says that it is more than 4%. So let's see what happens. Part B says, for a particular shipment, suppose that 27 of the inspected caps, out of the 500, 27 are defective. State and interpret the conclusion of the test. All right. So we have to calculate the test statistic first that we talked about a few slides back. Here's the test statistic that we have to use. X, in this case, is the 27. N is the 500. And P naught is 0.04. So let's calculate the test stat here. So the test stat comes out as 1.6 when you do the math and replace those parameters with the numbers. You get 1.6. So basically, this is a z-test, and it's a one-sided z-test. And this is the critical region. It looks like our test stat is 1.6. Let's find the critical region. Well, the critical region is same as all the z-tests for one-sided, is when the test stat is more than z of alpha. And in this case, z of alpha is z of 0.1, which you can read from the table. Z table is 1.28. So we reject the null hypothesis if Z score is greater than 1.28. Basically, this point right here, where the critical region begins, is 1.28. And looks like our test stat, 1.6, is above that in the critical region. So we are here. And since test score of 1.6 is greater than critical region, critical limit of 1.28. The conclusion is rejecting the null hypothesis. And rejecting the null hypothesis means that we are rejecting this hypothesis that population proportion is 4%, and essentially we are accepting the alternative hypothesis. It is more than 4%. So we reject the entire shipment essentially and sending it back to the supplier. That's what happens. We could conclude the same using the p-value, computing the p-value of the test. If you remember, and you can take a look at the hypothesis testing reference guide PDF on Blackboard, where you can calculate the p-value, and for a one-sided test that we have here of type greater than, it is equal to probability of z greater than z score, and that means probability of z greater than 1.6. Well, you can read that probability by doing 1 minus probability of z less than 1.6, and you can directly read that part from the z table, and that is 0.945. Therefore, the p-value is 0.055. This is the p-value, and when the p-value is less than alpha of the test, we reject the null hypothesis. In this case, the alpha of our test is 0.1, and the p-value here is less than that, so we reject the null hypothesis. So we say since p-value of 0.055 is less than alpha of 0.1, we came up with the same conclusion that we had here. Reject the null hypothesis. And this is important. Always, these two methods should give you the same conclusion. If you end up with a different conclusion using any of them, that means you probably made a mistake somewhere. So, part D says, what is the power of the test? You know, power of the test is 1 minus beta. Beta is probability of type 2 error. 1 minus that is power of the test. When P is equal to 0.08. Essentially saying that if we estimate that the population proportion, the proportion of all these defective caps is 8%, if that's a good estimation of the entire population, what is the power of our test? What is the power of this test using this n and all the other characteristics? So we need to calculate beta for this test, and this is a one-sided test, as you can see, of type more than. If you go back a few slides here, you can see how to calculate beta for that type of test. We have the p, it's given, it's 0.08. We have the p naught, 0.04. This is our hypothesized value. We have the alpha, we have the n, 500, and everything else. We can calculate this beta. So let's go ahead and do that. So here, if we replace all these parameters to calculate beta with the numbers that are given here, then do the math, you get to probability of z less than or equal to negative 2.37. Now you can read that from the z table, and when you do that, you'll get 0.008894. Very small percentage. And that's the probability of type 2 error, beta. And type 2 error is probability of failing to reject the null hypothesis when the null hypothesis was false. And 1 minus beta is power of the test. So 1 minus this number is about 0.9911, and that is the power of the test. And remember, to calculate beta, you need to have the population proportion. It should be given to you. Part E, it says, if the producer wishes to have a type 2 error probability of 0.05, well, now if we want to have a beta of 0.05, when P population proportion is 0.1, then what sample size should they use? Let's say that they want to have a probability of type 2 error of 0.05, which is actually way above the number that they have right now with this test, because this is the beta right now. But they're saying that if they want to have a larger beta, basically loosening up their test power, and they know that the true population proportion of defectives from the supplier is 10%, then what sample size do they need? Well, to calculate the sample size, again, if you go a few slides back, here's how you calculate the sample size when you have this type of test. Again, you have the P, in this case is 0.1, and P naught is 0.04. You have the beta, it's given to you. Now you can calculate the Z of beta. And the rest. So let's calculate N here. Well, to calculate N, we have these parameters. We need to read Z of alpha, which is Z of 0.1 from the table. We already know that is 1.28. You need to have Z of beta, and that is Z of 0.05, and that is 1.64 or 1.65. And replacing all those parameters in the formula and doing the math with the P and P naught and Z values, you will get to 154. And that is the required sample size to satisfy beta level of 5% when the population proportion of defective is 10%. So basically you can see that they can collect less sample. In this test they were collecting 500 and testing them. Now if they have these criteria, then they can go with a smaller sample size, which is less costly to do that test.